We humans deliberately seek out spicy foods, and despite the painful sensation, we come back for more. So, what causes this irritating sensation? Capsaicin is a pungent molecule in chili peppers. It is composed of a vanillyl group, the head, an amide group, the neck, and a fatty acid chain, the tail. To elicit the spicy sensation, capsaicin excites nociceptive or pain neurons by binding to a channel called TRPV1, transient receptor potential vanilloid 1.
So, why is this important? 50 million Americans have chronic pain. Previous drugs for pain treatment have focused on preventing pain signals from reaching the brain. But now, with an understanding of TRPV1, we can pinpoint the detection of the nociceptive stimuli at the receptor itself. So we must understand the structure of TRPV1.
The structure of TRPV1 was elucidated by cryo-electron microscopy and computational modeling. The TRPV1 receptor is a transmembrane protein with 4 subunits. Each subunit is composed of 6 alpha helices, S1 through S6. At the N terminus is an ankyrin repeat domain, a 33 residue sequence believed to interact with proteins. A linker domain connects this segment to the pre-S1 helix. The S4-S5 linker connects the S4 and S5 helices. A P-loop composed of a short helix and a loop link the S5 and S6 helices. Arranged radially, the 4 adjacent P-loops of all the subunits, together with the S5 and S6 helices, form a central pore and selectivity filter through which ions pass through. The TRP domain, a helical segment found in all TRP receptors, connects the S6 and the C terminus. This helix forms hydrogen bonds with the pre-S1 helix and the S4-S5 linker. These interactions allow the TRP domain to act as a site through which pore conformation can be allosterically modulated. Rigid hydrophobic packing created by the mostly aromatic residues of the S3 and S4 helices allow the S1-S4 domain to function as an anchor. The S4-S5 linker moves about this anchor to open and close the TRPV1 lower gate. The TRPV1 receptor has 2 gates, an outer pore region known as the selectivity filter and a lower gate. When no capsaicin is present, the receptor is constricted at both the selectivity filter and the lower gate, blocking ion permeation. The lower gate is formed by hydrophobic interactions between S6 helices from each subunit. This gate narrows the width of the lower part of the channel, blocking hydrated ions when the lower gate is closed. In the closed state, the selectivity filter is less than 1 angstrom in width, which is too narrow for hydrated ions to permeate. When capsaicin binds, both the selectivity filter and the lower gate are dilated. In this fully open state, the selectivity filter is still the narrowest part of the pore, which ensures that only sodium and calcium ions can pass. The capsaicin binding pocket is formed by the S3, S4, and S4-S5 linker within the membrane. During capsaicin binding, the tail contacts the upper half of helix S4 to form non-specific van der Waals interactions. In the absence of capsaicin, the tyrosine 511 on the S3 points away from the binding pocket. When capsaicin enters the binding pocket, the tyrosine 511 rotates to point into the binding pocket as it interacts with the vanillyl head, inducing the fit of the capsaicin in the binding pocket. At the same time, hydrogen bonds form between the amide oxygen atom of the capsaicin and the threonine 550 on the S4 helix. Capsaicin pulls at glutamate 571, stabilizing the S4-S5 linker in its outward conformation. As the S4-S5 linker swings outward, helix S6 follows behind to open the lower activation gate. This motion exposes hydrophobic residues on S5, S6, and the P-loop that form the selectivity filter, causing it to dilate. Sodium and calcium ions flow in and depolarize nociceptive neurons, creating action potentials that travel to the brain and cause the sensation of pain.
Besides capsaicin, TRPV1 can be activated by many physical and chemical stimuli such as noxious heat, acidity, divalent cations, and animal toxins. The activation of the TRPV1 channel will then lead to nociception. By elucidating the mechanism of capsaicin binding to TRPV1, we can develop drugs that inhibit the activation of the receptor through competitive binding, blocking nociception at the source of the pain stimulus. Therefore, future work in this field includes developing an inhibitor of TRPV1 as an analgesic.